In this session, we like to look at a very commonly seen manner of presenting distributions, and this is called the tabled distributions. It's actually not an official name except for the fact that it is often presented as a table. Why table? Whether it is giving exam question or presenting customer reports or or discussing researched information in a board meeting or presentation to investors. Oftentimes, we like to show a lot of hard work, quantitative hard work and results done in a way that's as compact as possible, yet not losing a lot of fidelity. That means we're throwing away too much details until nothing comes out. So we don't want that. So we want enough details, but a broad picture. So turns out tabled distribution is the very, very common way, an acceptable way to perform that kind of communication of humongous amounts of quantitative outputs. So we can therefore also describe a probability distribution in a tabled form. Yeah, so we will say that the x values, for example, in this case, will take up 1.7, 3.25 point. Now I purposely give these numbers to challenge your mind, right? To make sure you don't settle with a integer value, 1, 3, and 5, as if there has to be some sort of a regularity to it, as if it has to be, a very obedient integer. No, it doesn't have to be. It can be a label even. It can be, a fixed real number like 1.7, 3.2. So all these are considered, of course, discrete points. Discrete points. Frequently also, there is no easy function to go from one point to another. For example, you don't say 1.7 times 2, you get 3.2. No, not really, right? So these numbers, they are usually either very localized to that application. For example, maybe these are the values obtained from fragrance experiments. So those are the numbers. You cannot change that, right? Or those are the numbers that are measured by an instrument, and so that is the way it is, right? Or else it would be just arbitrary situations. They are labels, so red, green, blue. So no matter why the values are described the way they are, we give the probabilities accordingly for each value. So again, those are just points. So 1 point, 2 points, 3 points. For aesthetic reasons, we not only draw the height, but we also fatten the height. Yeah, so those are just making it pretty. You need to read these histograms and diagrams with X-ray vision. That means you are mentally going to not be distracted by the widths. That's very important. So how to calculate the probability? Very easy. Just look up. What's the probability of 1.7? Just check out. There's no other way. You cannot use a calculator, plug into a function, x squared minus 3x. You cannot do that. So you just look up the table and you get 0.25. What's the cumulative probability, CDF, of 3.2? Well, that's 0.25 plus 0.45, so that's 0.7. Yeah. What's the probability of 1.9? We try to look it up, not there, so 0. Yes, 0. Yeah, okay, it is not 0.25. But what is the CDF of 1.9? Then yes, 0.25. Yeah, so those are easy questions about probabilities. What about expected value and variance? Well, that's the same as what we have done using Excel in the grouped sample data discussion. So exactly same calculation using sum product. So very easily you get 3.605 and so on. So when do we apply them? Many cases. When there are predetermined outcomes, exhaustively listed outcomes. Yeah, sometimes we decide what's the outcome. Yeah, so choose red, green, or blue. You ask the customers. So that's the predetermined outcome, right? Exhaustively listed outcomes. Okay, we also have pink and purple. Might as well just give it to them. No, I don't think they will want. So let's not show it to them. No, show it to them, So if you give everything, then that's exhaustively listed. Experiments which measure frequencies of occurrences. Sort of like the third row here, I show it just for assisted understanding. So normally the third row is not given. But if you're doing experiments, you're counting successes, right? Counting the observations that give you 1.7, 5 times. So you do that, 5, 9, and 6. And then you divide by the total to get a relative frequency. So that's 5 over 20. And you get 0.4, 0.25, and so on. And then you relabel the relative frequency, because that's past, to future, and call it probability. So this will be how we derive these probabilities right now. Yeah, so we're using past data frequencies to assert the future. Now, basically, that's it. But what I want to show you is a little bit of a connection between sample measurements. That means we measure, we record the numbers, histogram, and distributions. So I like to just pull in this chart here. We can see it. All right. So what I did was to create a histogram, and which will automatically update itself. So I've done this part. And I want to, what is this? Okay. So what I want to do is to also do this. Let me see if I got it right. One, two, three, four, five, six. Okay. And if we start to fill up the frequencies, how many times did I see the x, the measured value, being observed? No time. How many times did I see x equals to 1? One time. 3, 3, 5, 8, 10, 9, 6, 7, 4, 2, 1. So you see that a histogram starts to build up. Yeah, so because I filled in the frequencies like this. Now, it is possible that you might ask, where do you get the frequencies, right? How do you know it's 0? How do you know it's 1, 3, and all that? It comes from a long tabulated, repeated records of x values. So it can look something like this. Let me, by way of also, let me see, where do I put it? Here. So by way of generating a bunch of Bernoulli data. So what I'm going to do is I'm going to generate a bunch of zeros and ones, okay, like this. So I will get a bunch of zeros and ones, and I measure 0, 1, 0, 0, 0. Like I'm throwing a coin. First time, second time, third time, fourth time, fifth time I see a head, and then tail again. Head, and then tail again, and so on. Yeah. So I get, well, I should repeat this 1,000 times, but here I've generated how many times? 16 times, just so that it doesn't take up too much screen space. And then I will perform a count if. Right, count if takes in this blue box, the entire set of values, count for the occurrence of zeros. Yeah, and then I will copy and paste this number to the next one to look for any value that is equal to 1. And of course, I don't need to do that for 2, 3, and 4 because I know it's never going to happen. So here I will then paste this as a number 11 and 5 and erase the rest. And so here is my Bernoulli distribution, where 0 is what? Is 11. 11 counts, and 1 is 5 count. Why is that? Because my population proportion of ones should be 30%. Now I don't really get 30% because I only get 16 sample size. So if I do a lot more, then I definitely will be able to get a much more representative or proportion of ones being closer to 0.3. So likewise, for binomial distribution, we can end up getting this kind of frequencies. Yeah. So again, this is n equals to 12, p equals to 0.3 also. So for throwing 12 coins, yeah, and I end up seeing 8 times. One time I get 8 coins showing heads. Yeah, and then 5 times the coins. No, sorry. 5 times the coins show 6 heads out of 12 coins, and so on. So that will be a very rough binomial picture. And of course, we can also do a Poisson distribution. Uh, and then I will just show you the frequency of lambda equals to 2.5. So in that case, the average should be somewhere between 2 and 3, 2.5 there. If I continue to do the experiment many times, in this case, my experiment was done for just not much, 21 times. So it's not going to average to 2.5, but more experiments I do, the frequencies will be much higher. Then I'll be able to get a 2.5. So the frequency here should, of course, be standardized, should be divided by the total count in order to arrive at fractional frequencies. But for simplicity, it will just be too complicated. So for simplicity, I simply show the frequency. But again, you should remember that the shape wouldn't change if I rescale the y-axis. It would just be a bit taller, fatter, or skinnier, but it will not change the shape of it. So this is how we can go from frequency to relative frequency to probability. So here is a completed version, okay, where a lot more calculations are involved. We go from frequency to relative frequency. Yeah, so the shape is exactly the same, but instead of calling it frequency, we relabel the y-axis and scale the y-axis. But you see that because when you scale it, it becomes very tiny, so we magnify it to show it properly again, so the shape doesn't change. And finally, by changing this label alone, the how we call the y-axis alone, in one fell swoop, we went from past and known to future and unknown by just simply calling it the probability of events. So everything is the same, shape is the same, height is the same. Instead of calling it frequency, we change to relative frequency and rescale the y-axis. Those are still in the past, still in the known. Change the label, call it probability, then it can be used for future for the unknowns. So again, this summarizes and concludes our discussion about standard distributions. I hope you enjoy the insights given here. See you in the next video.